We're now recording. And okay, Martin, would you like to introduce our speaker? Can people online hear?
Hello, testing.
Yes, I can hear Ari.
So it is with great pleasure that I welcome Xiteng, who is a senior undergraduate in the ECE department at BU and has been working on this project. Since June, and worked through the summer, and now is working part-time on it, and will continue through graduation. We're very pleased. So.
Yeah, I would like to thank the Red Hat for providing the funding for my research, and also thank to my mentor, Professor Herbert, and my collaborators at the UCAD Lab and Red Hat Research. Thank you so much. So our project focuses on the FPGAs. FPGAs are field programmable gate arrays. It's a type of hardware that usually has millions of logic gates on it. It could be reprogrammed after manufacturing, and this is its advantage over application-specific integrated circuit or ASIC. These FPGAs are programmed using register transfer level designs or RTL designs. It can outperform CPU in many important applications, like on cloud computing, enterprise networking, data mining, AI acceleration, and hardware acceleration in many other specific domains. This diagram shows how FPGAs could be used in different stages in cloud computing. The FPGA industry market is estimated to be.
I think since we're recording, maybe we'll record the whole presentation, then we'll stop the recording.
It's small.
Yeah.
So from the industrial perspective, FPGA market is estimated to around 8 billion and grows at 14% per year. This shows the great potential of FPGA's application in wider areas. These two diagrams are two pictures of FPGA manufactured by Xilent. This has a PCI connection, which means it could be connected to a PC and be used as hardware accelerator, similar as GPU. So there's a critical problem in FPGA, the programmability problem. An ideal platform should be performance, programmable, and portable. However, it is hard to get all the three P together on FPGAs. Research has found that it's very hard to program FPGA to maintain its high performance. Developers need to be very experienced and learn a lot about hardware description languages. As a solution to this programmability problem, the concept of high-level synthesis was brought up in the 1980s. In high-level synthesis, like the diagram shown there, the high-level code, like C or C++ code, is transformed by the HOS process to RTL designs, which could be directly mapped to the FPGAs. This process significantly reduces the difficulty of FPGA programming.
Only this using both C and
And researchers suggest that it has the potential to completely replace the traditional RTL design process. And HOS is not perfect. We find that although HOS makes it more programmable, but it has a performance issue. A prior research at BU has shown that HOS generated RTL designs has inferior performance compared to human coded designs. This makes the HOS process unusable in large commercial or scientific applications. Therefore, our research aims to improve the performance of HOS generated designs. To do this, we consulted a prior work at UC Berkeley. They are using the compiler optimization process. Compiler optimization process are the programs that transform the code and try to make them more efficient when running. This shows an example of how they are applied in an LLVM compiler. High-level code like C or C++ are transformed first into an IR, and the compiler optimizer applies optimization on it. The IR is then sent to the compiler backend to transform into executable. And in our applications, the optimized IR sent to the HOS backend, which are transformed into RTL designs and can be mapped onto FPGAs. However, compiler optimization processes are code specific. Some of them will applying the wrong compiler optimization process will negatively impact the performance of the program. So it becomes important to select the correct ones to apply. To do this, the prior work at UC Berkeley is using a random forest reinforcement learning approach. To expand their research, we're using two approaches. First one is supervised learning, and the second one is reinforcement learning with different strategies.
What are you learning? Talk about that.
So we're trying to predict the best optimization process based on the input code. So this process could be applied to the code to optimize it.
Oh, can you repeat the question? The question was, what was being optimized?
The input code.
No, actually, your answer was precise, the first thing you gave. This is called the phase optimization, the phase ordering problem. And it's a fundamental problem in compiler optimization.
So in supervised learning, there's a supervised learning model that learns from the label data. The model after training tries to make predictions that as close as label as possible. And in our application, there are some limitations to the supervised learning, like there's limited amount of label data, and there are not many databases suitable for training. But despite these problems, we're still use supervised learning, since we try to figure out how to ameliorate these problems. And also we'll try to get a framework for testing new feature extraction methods. The dataset we use is the Rodinia benchmark dataset. Okay. So we're using the Rodinia benchmark set. Rodinia benchmark has many benchmarks that are used in different domains, like medical imaging, bioinformation, fluid dynamics, or so. The Rodinia benchmark itself is very diverse, as the diagram shows here. It has different characteristics of optimizations, so we think it could be used for our application. By the feature extraction, the prior work used there's a prior work called Code2Sig. They use the abstract syntax code, or ASTs. AST has very important information of the code, like declaration, assignments, operations, and conditional statements. For example, the simple code on the left counts the number of occurrence of the value in the source string, and its AST is shown on the right. The simple code could have the simple AST trees could have 100 of passes. By passes means starting from one terminal node and go to another terminal node. The Code2Sig paper fit these passes into their models and train their data.
What is it?
So this is the tree data structure, right?
Yeah.
And they have like the pathfinder that go from one terminal node and go up and go to another terminal node.
Right, but why? Why do we care about this?
Well, the prior research at Code26 shows that this passes has the features of the code. You can actually learn from these passes. So this is a method of feature extraction.
How do you talk for a minute about the significance of feature extraction?
Yeah, so in supervised learning, the label data must be extracted, like the feature must be extracted to put into a machine learning model. The data itself, in our case, is the input code, which cannot be encoded efficiently into vectors that could be put into machine learning models. So this is the machine learning model. We look at the code-to-SIG model and the seq-to-SIG model. We redesigned the decoder to predict the best optimization passes. The AST pass here is put into the encoder here, and alongside with subtoken information. Each pass go to a separate encoder and pass to the dense neural network. For example, the program here could have like 100 of these things, and there's an attention decoder that's there's an attention decoder here that assigns attention to this data passed through the neural network, and based on this data, they generate a sequence of optimization passes. This kind of model, encoder decoder model, is usually used in natural language processing. And to evaluate our results, we're using CPU runtime due to our limited time. We're comparing the runtime of the code optimized by our machine learning model and the standard optimization approach, which is -03 flag and unoptimized code. This shows the results. An earlier result shows that in most cases, we can achieve 15% of runtime reduction. And this is the updated model, which shows better results, but we haven't tested on all test cases. So in this cases, the Needleman one-shot test case performs better than the -03. And in Spring Cluster and SRAD, it could significantly reduce runtime. And in some rare cases like Pathfinder, neither our approach or the -03 approach could reduce runtime. It's in seconds. And during our research, we developed a data labeling algorithm, and it could automatically data with reasonable time. This partially solved the data labeling problem. For reinforcement learning, in reinforcement learning, we have an agent that interacts with the environment. The environment gives the agent feedback, and during training process, the agent evaluates the feedback and updates the policy. The policy helps the agent to maximize the long-term reward. And when rolling out, the agent uses the policy it learned and try to predict the best results. This entire process is basically a trial and error process. The advantage of it is that it does not need labeled data. So in our applications, we're using a PPU agent, and in each step, it applies one or several optimization passes and evaluate the cycle counts as a reward. Prior state-of-the-art work, Autophase claims that they achieve 28% better performance than compiling with -03 flag. This shows that it is possible to use RL to do this. However, they only measure the speed up over -03 and omit other performance metrics. For example, the learning speed, performance potential, and the fluctuation band. This diagram shows a typical run of reinforcement learning and how these metrics are calculated. Another problem of their work is they only have very limited number of strategies. And prior works in reinforcement learning shows that different strategies could lead to different results. So we also tested on different strategies. We developed these strategies by changing the action state, episode length, and reward frequencies. This is the result of our reinforcement learning. The blue line here is the base case, which is the autophase work. And we measured all of our strategies using this test cases and show different metrics here. So that are the performance metrics.
So higher is better?
Yeah.
0 1 4. Because 2.5 is one looks like it's the biggest.
Yeah.
It's normalized against the largest.
Yeah.
So it's not fair that we can compare the those at all.
Yeah, that's true. So we're only comparing our work to the base case. We're showing our approach is better than the autophase based on in different applications.
But it looks like one is always the best cases, you're not comparing the best. We normalize the best case for one, everything else. That's what it looks like.
Yeah.
So I think that you could explain again what the strategies are, and so that the two things that you're kind of doing at the same time. Why don't you go through this backup one?
So by this matrix, the maximum reward is the maximum reward we've seen, and the learning speed is the peak of the reward we have times by 0.9. And when the agent reaches that reward, just pause and count that time. So we get the learning speed. The fluctuation band is the fluctuation between the max and min after a certain time round of iterations. And the performance potential is the peak reward, percentage of the maximum reward thing. And speed up over O3 is comparing the reward based on the dash O3 line.
Oh, okay. The graphs, it wasn't clear how you compared the flow of each other.
So the idea is simply that whenever molecules form one, then one of the other strategies is better.
Right. So you're normalizing based on the best strategy.
Yeah. The graph shows that the base case, the autophase work, could have like inferior performance in different metrics based on application. So the conclusion is there's no one-size-fits-all solution, and choosing the right strategy is very important. We summarize the best strategies we found in terms of different metrics and different applications. So our work has shown that there's a potential to improve the performance of actual standard designs using machine learning, and reinforcement learning could be used to avoid problems like inadequate label data. And the choice of strategy in reinforcement learning is vital. Since this is an ongoing research, there are still a lot of things to do. For the supervised learning side, we need to try new feature extraction methods, improve on the data labeling algorithm. And for both supervised learning and reinforcement learning, we need to test on larger data sets. And for future research, we could change to semi-supervised learning, test with latest compilers and HOS tools. We could also build a recommender system for optimal strategies.
Thank you.